The human eye registers a hazard. A signal travels down the spinal cord. The leg muscles contract, and the foot hits the brake. In an emergency, pushing this biological sequence to its absolute physiological limit takes roughly a second and a half. At highway speeds, a vehicle travels over 100 feet in that time before the brakes even begin to engage. This physiological delay accounts for the majority of vehicular accidents globally. Advanced Driver Assistance Systems, or ADAS, are an engineering solution built to correct this biological bottleneck. This timeline compares the biological and machine control loops. While a human relies on eye, brain, and foot, the machine utilizes a sensor, ECU, and drive-by-wire brake. This mechanical system reduces latency to fractions of a millisecond, reacting faster than biology allows. Understanding this system requires deconstructing it from the ground up, moving from hardware perception to algorithmic processing, and finally to the taxonomy that defines true autonomy. ADAS represents a cyber-physical redesign of the driving control loop, engineered to bypass human fallibility through precision hardware. While a human driver uses stereo vision to understand their environment, a machine requires a diverse, overlapping array of physical inputs to perceive the world safely. The perception layer begins with optical cameras identifying lane markings. Radar modules emit radio waves to measure distance and velocity regardless of light. Ultrasonic sensors provide short-range echolocation for close-quarter maneuvers. Finally, LiDAR bounces laser pulses to construct a precise 3D point cloud map. Effective navigation requires the vehicle to establish absolute geographic context beyond these local inputs. Global positioning satellite constellations provide constant latitude and longitude telemetry, pinning the vehicle's exact location to a digital map. By utilizing this multimodal sensor array, an autonomous vehicle creates a fail-safe perception layer where one sensory input compensates for the limitations of another. High-definition video, radio wave returns, and laser point clouds moving at light speed create massive data overwhelm. This raw sensory data is useless noise unless the vehicle has a way to interpret it instantly. This introduces the brain of the system, the Electronic Control Unit, or ECU, which operates on a powerful system-on-a-chip architecture. This visual equation demonstrates sensor fusion. It is an AI-driven process that merges disparate data streams. If a camera is blinded by glare, but the radar detects an object in that exact location, the ECU merges the data and confirms the obstacle. Sensor fusion mimics the brain's ability to synthesize sights and sounds, executing calculations exponentially faster. The ECU produces a constantly updating 360-degree unified 3D map, plotting a single ground truth that predicts the trajectory of every moving object. Safe autonomy depends entirely on the ECU's ability to reach these computational conclusions in milliseconds. Once the environment is mapped, the ECU must translate digital decisions into mechanical actuation, manipulating the steering column, the brakes, and the throttle. Automotive safety systems are divided into two categories. Passive systems warn the driver using audio and visual alerts. Active systems physically override the driver to prevent an accident. This diagram illustrates active longitudinal control. Through adaptive cruise control, the trailing vehicle calculates distance and autonomously modulates speed. If the lead car stops abruptly, automatic emergency braking bypasses human hesitation, applying maximum brake pressure the millisecond a collision is detected. Actuation also manages lateral control. Electronic stability control detects the early stages of a skid and intervenes to prevent understeer or oversteer during emergency maneuvers. If a specific wheel loses grip on a sharp curve, the traction control system independently applies brake pressure to that tire, maintaining grip. Crosswind stabilization takes this further, detecting lateral wind offset and automatically distributing wheel load to maintain the vehicle's course at high speeds. This specific crosswind actuation technology first reached consumers in production vehicles in 2009. For lane management, Lane Centering Assist analyzes road markings from the front-mounted cameras and proactively manipulates the steering column to keep the vehicle centered. Together, these active actuation systems form a mechanical safety net, executing physical corrections with a level of precision that human reflexes cannot match. Having established the hardware and software architecture, we can map these capabilities onto the industry standard spectrum defined by the Society of Automotive Engineers. This matrix outlines the 6 levels of automation: At level 0, the human driver is entirely responsible. Levels 1 and 2 introduce driver support. At level 1, the ECU handles steering or speed. At level 2, the vehicle controls both simultaneously under specific conditions. At level 2, the human remains legally responsible. Level 3 manages tasks in specific conditions. The driver can disengage but must respond to takeover requests. Level 4 performs all driving functions without human intervention, constrained only by geofencing technology. Geofencing restricts Level 4 vehicles to designated routes or mapped urban centers. If the vehicle leaves the geofenced area, autonomous operation is disabled. The SAE taxonomy illustrates the precise moment the burden of environmental monitoring and physical control transfers from the biological brain to the machine's processor. The ultimate engineering objective is an environment completely devoid of human controls. This is SAE Level 5, automation on any road requiring zero human attention. Achieving Level 5 depends on moving beyond the data provided by an isolated sensor array on a single car. This necessitates a decentralized network architecture, where vehicles exchange data instantly through vehicle-to-everything, or V2X, communication. This city grid shows a V2X network. Vehicles wirelessly broadcast data to other cars, vehicle-to-vehicle, and to infrastructure. When a vehicle encounters an accident, an alert transmits backwards, allowing a V2X-equipped car to react to an obstacle miles ahead. ADAS begins as a system to support a human driver. Its evolutionary trajectory, however, is to replace the human driver completely. Integrating onboard sensor fusion with instantaneous V2X communication links millions of isolated machines into a unified network, removing the biological variable from the driving control loop.